So I see something in its derivative, which was the first thing we ever learned in here, like basic U substitution. That's basic U sub now. This one is the previous type where you have a constant over an irreducible quadratic. So I got more work to do, all right? Here we go. For this one, I know that the bottom is U, the top is du exactly, right? So this integral really looks like 1 over u du, and the antiderivative should be ln, right? ln of this whole thing, right? Natural log of that whole thing. Now we do have a 1/8 in front. So this whole thing becomes 1/8. I'm doing the actual antiderivative mentally here. I mean mentally as in the sense that like I know that that's what's going to happen because again that's the way I designed the integral is so that it would be something like 1 over u du.
How did you see the top as 1?
The top is 1?
You saw the top is du.
Like,
You see what I'm saying?
yeah.
Are you you're still in? Oh, you're good. Okay. Yeah, it's right there, right? Other questions? I'm not done, right? I'm going to go ahead and take this negative form, pop this out. So I still have minus, let's see, 4 over 8, so half. So I have a half, and I still have to deal with this integral over here. You know, sad for me. Look, and like I said when I started this problem, there are other methods to do this, and I will admit that some of those methods are a little faster and a little less confusing, I guess. But I really do think that it is an important trait of whatever it is, you know, engineering, computer science, whatever it is. I think it's an important trait to see this sort of thinking in a problem. Like, I'm going to make something become what I want it to be, right? So it works the way I want. Like, you actually have a little bit of control here, right? You can manipulate things however you want to manipulate them, as long as you don't break any rules, right? All right, so I'm done with this part. I really just need to focus on this integral right here. So why don't we go complete the square? Why don't we go complete the square? I'm going to take this 4x squared, what time is it? Yeah, minus 4x plus 3. I'm going to complete the square. So I'm completing the square. I need to pull a 4 out first. Right, that's the first thing that has to happen is I have to have coefficient of a 1 there. Ooh, shoot, man, we're going to have fractions, aren't we? Okay, so we have x squared minus x. All right, we take the number in front of x, which is negative 1. We take half of it,
So
negative a half, right? You're taking the number in front there, negative 1, and you're taking half of it, right? And then you're squaring that. When you square that, you get a 4th. So add and subtract 1/4. Add a 4th, subtract a 4th. And then you still had a 3/4 there, right? Plus 3/4. The first 3 of these are guaranteed to factor to be something squared. And remember what I told you that number would be, right? It'd be that thing that you take half of. So x minus a half. And then these two together, 2/4. 2/4, which is 1/2. How we doing? How did I get the adding and subtracting it? So when we complete the square, the first thing we do is we make sure there's a 1 coefficient, right? Then whatever number is here, we're going to take half of that number. So I take negative 1, I divide it by 2, right? And then you square it, so you square top and bottom, you get 1/4. All right, I think I'm ready to pick up right here. I'm going to pick up right where we were. This is going to be equal to, I'm going to go ahead and write the first part out. 1/8 natural log. I've already done this part, right? This integral is done. right, now I have minus a half integral, and then I completed the square on the bottom here, so it's 1 over, and now the completing of the square of that is this. Notice I have a 4 out front of everything. Okay, so I'm going to have a 4 in front of x minus a half, that's being squared, still have plus a half, that dx. That's the completion of the square of this. Can I pull this 4 off the bottom?
Yeah.
Yes. So that'll become a 1/8 out there. We're close. We're close to being there. So 1/8 natural log 4x squared minus 4x plus 3 minus 1/8 integral 1 over. I don't need the parentheses anymore on that because I pulled the 4 out. Finally, it is to something I can do something with. That's what? Formula 17. If you did a quick U sub, right? And we wouldn't have to scale, would we? Because the U sub we would make would be x minus a half, and that has a 1 in front of the x, so you wouldn't have to scale. Does everyone see the U sub here? I mean, not the U sub. Formula 17, where this is the U. Now, what's A? Square root of a half, right? That's squared. That's A squared. I mean, sorry, that's 1/2 squared.
Could you, if you didn't know, because I didn't know that, could I have just left it as square root of 1/2?
Oh, I'm going to leave it as square root of 1/2. Well, if instead of what?
1/4.
It's not 1/4. The square root of 1/2. What I would expect you could do is just take the square root of the top and bottom. That's what it is. Now you could rationalize this and make it root 2 over 2, but it's not necessary. Okay?
Oh, yeah, okay.
And if you left it like that, I wouldn't be like, if you got all this right and that you left it like, I'm not going to be like, you know, because it's still right, you know. Okay, I'm ready. This is the answer time. All right, it's going to be 1/8 natural log of 4x squared minus 4x plus 3. Okay, and then I have minus 1/8. That's this part. Okay, I don't have to scale this, right? I don't have to scale this, the answer, because there's a 1 in front. But I do need, the formula has 1 over a, doesn't it? 1 over a. I'm just going to write it, and then I'll maybe clean up next line. It's 1 over, a is 1 over root 2. Right, that's a. It was the square root of that. So 1 over root 2. Inverse tangent of x minus a half over a 1 over root 2 plus c. Box it up.
You don't want to
I can do other stuff. I can do other stuff.
e times root 2 times x minus 1/2?
You can.
Okay.
You can. If you go and look at like an answer in a book, it's probably going to have done something like that. They'll probably rationalize. Should we check our answer? Take the derivative?
I believe you.
No, I believe me too. I'm not going to check that. That seems like a nightmare. But, pretty interesting problem, right? Because to do this problem, we eventually had to complete the square, didn't we? We eventually had to do like a constant over irreducible quadratic. We eventually had to do it. It was just that first step of trying to massage the numerator into what we wanted it to be. That's kind of like the unique step for this problem. So I always ask my students if they want to see it the other way or not, or if we just want to stick with this. What do y'all want?
So you, from the beginning, you got you did like a use of to get the derivative of the denominator.
Yep.
And then from just looking at what the derivative would be, that's how you pretty much formatted.
Created the numerator, made it turn into the denominator's derivative, yeah.
But you use that first, like constant that's actually it. So like the 8 in this case.
Yeah. I can do another one. at least get it set up. Yeah, let's do one where we just at least set it up. We may not go through the whole thing, but at least get it to the point where it's two integrals. Yeah? Was that a question?
Yeah, I
Oh.
think it's a stupid question, but
You know, they say that there's no such thing as stupid questions, right?
yeah.
I don't believe that. I do believe there are stupid questions. I think that's something that you say to be politically correct. So be careful here.
That left integral, remember how you just take it to like 1 over u and du and all that? Like, is that just intuition, you just saw that? Like,
Well, it's because that's the way I designed it. That's the way I designed it. Okay, let me do another one. Maybe as I'm going through it, I'm going to try to force that idea a little bit better. All right? So on this one, I'm just going to make one up. I have no idea what's going to happen here. You have to be careful with integrals because you can create a problem for yourself if you're not careful. But I'm going to hopefully not mess this up. All right, so let's go with, how about we have, I'll keep it relatively okay. Let's say we have x plus 3 over, okay, so the way I'm designing this is I'm putting a linear expression up there. And now what I'm about to do is give you a quadratic on the bottom that's not factorable. Take it easy. So I'm going to do x squared, and I'm going to be nice to you. I'm going to put a number in front of this so that when we do the completing of the square in a minute, it'll be a nice number there that you take half of and square. Okay, so and then I'm just going to make sure it's not factorable. So I'm just going to put this plus 1, and then I know that that doesn't factor. All right. So first thing I do is I look at this and I have to realize I have a linear expression on top of an irreducible quadratic. That's linear and that does not factor. I have to see that to begin with. Once I'm there, I'm going to use the method of making u equal the denominator. I'm going to make a basic u substitution. U is equal to x squared plus 4x plus 1. Then I'm going to take derivative of that. And I get 2x plus 4 dx. Everyone on board with that?
Is your u typically the denominator?
It's always the denominator. Well, when I'm doing these problems, the way I do them is if I see a linear over an irreducible quadratic, I can't stress that enough. If this factors, we're talking about next Tuesday. That's what we will, if this factors, we have a totally different way of doing this, all right? But if it doesn't factor, this is what we do, all right? So I'm sitting here, I'm like, okay, let u be the denominator, boom, every time. Look at the derivative of it, and then sit here and scratch your head and go, how can I turn this into that? Why? Because look, what if I had this? What if this is what I had? What if that's exactly the problem this whole thing started off as? I would let u be the denominator, right? The derivative of that is 2x plus 4, which is exactly the top, right? So this is just 1 over u du, isn't it? Yeah. And then that's just natural log of the absolute value of u, but what's u? That. Do you see that? So it's like, this is what I wish was up here, right? And it's not. So I'm going to make it be there. I'm going to make that become 2x plus 4. Does that make a little more sense? So now it's just I just need to be a little magician here. And first thing I'm going to look at is I need 2x, right? I'm always going to look at the coefficient in front of x first. That's what I'm going to force to happen. So to make that a 2 in front, I have to multiply by 2 over 2. You can't just multiply by 2. You have to do 2 over 2 because 2 over 2 is 1. So that doesn't change the problem at all. And now I pass just the numerators 2 through the top. And make sure you distribute that 2 to both terms on top. All I'm doing here is I'm algebraically massaging, manipulating the numerator into what I want it to be, right? That's all I'm doing. I'm closer now, right? I'm closer. I want it to be 2x plus 4. It's 2x plus 6. So you could at this point realize that 6 could be written as plus 4 plus 2, right? Yeah. You could. That's not the way I do it just because it won't always work out that way. Like sometimes this will be a fraction or something and then it won't be easy to do. So my next step every time that I do it is to do this. What is it that we wanted?
2x plus 4.
I wanted 2x plus 4, didn't I? So I'm going to write 2x and then I'm going to write exactly what I want it to be, plus 4. But if I'm going to add 4, I need to subtract 4. Right? So there's a hidden 0 that I've introduced. And then what was there? Because I mean, I did 2x, then I did the plus 4 minus 4, but there's still a plus 6 there. And then over x squared plus 4x plus 1 dx. These two come together to be a 2, right? And like obviously I'm not going to put them all together, right? If I put them all back together, I'm going to be back here, right? That's not what I'm trying to do. I'm trying to keep this 2x plus 4 so that it matches up exactly. Once I'm here, that's a natural place to split this into two integrals. These two terms over this, that term over this, and I think that's where I'm going to stop, but let me at least do it. Let me see, 1/2. I'll have this first integral is going to be 2x plus 4 over x squared plus 4x plus 1 dx. And then I have to do a half again, plus a half integral. And then up top I had a 2, and then it was x squared plus 4x plus 1 dx. Questions? All right.
No, I was wondering if I got it right.
Oh, okay.
No.
This one is good, right?
Yeah.
This one we know what to do with, right?
Yeah.
So
You sub that.
u sub, and we did it already. This will become natural log of x squared plus 4x plus 1, right?
Plus 1 over root 5.
Plus this, let's bring that out. Okay, let's bring the 2 out. It hits the half and it goes away. Integral of 1 over x squared plus 4x plus 1 dx. I still need to do this integral, right? So I'll complete the square on that. Real quick, I'll go ahead and do it. Real quick completing of the square. We take half of that number, which is 2, we square it, which is 4, we add it and subtract it. So add 4, subtract 4. And then we had a plus 1 there, didn't we? The first 3 terms factor to be x plus 2, that quantity squared, and then the other 2 terms come together to become a minus 3. What's wrong?
And we can't take the root of.
Yeah. Oh, no. It's because in the formula, it's it's your variable squared minus a squared. So you can look at that as root 3 squared. But we're going to not use 17, though. We're not going to use formula 17. Because 17 has a plus, right? We need the formula that's going to have a minus. So it's either 19 or 20. You see?
So it's 20, yeah.
But let me continue. I guess I'm taking this all the way, huh? This is equal to 1/2 natural log absolute value x squared, plus 4x plus 1. And then plus integral, we completed the square and we got that this turns into x squared plus, x plus 2 squared. I'm not talking right. That's my completing of the square of this, right? And then that, what formula is that? 20? 20. So this equals 1/2 natural log x squared plus 4x plus 1, close the absolute value, plus 1 over 2 times square root of 3. So in the formula 20 that we're using here, a for us is the square root of 3. Because this number has to be the thing that's being squared. Or this number is a squared. So the square root of 3 is root 3. And then natural log of, what is it?
X plus 2 minus root 3.
So it'll be, in the formula, it's x minus a over x plus a, or the other way?
X minus
It's x minus, so x for us is actually the x plus 2. And then minus the a, root 3. And then the x, and then plus the root 3. Plus c. There we go. That's it. That's it. You're done. I'm just curious to see what Wolfram gives us. So I want the antiderivative of a fraction. What did I give you? X plus 3 on top? On the bottom, it was x squared plus 4x plus 1 with respect to x. Do you see their answer up there? Okay.
Yeah, it'd be kind of hard to say.
Doesn't quite look like mine, does it? Doesn't quite look like mine. But here's kind of what's happening here. They're using a lot of different properties, but one property that I can kind of point out here is that when you have a log with division, you can split that into two logs with subtraction. So there's a way that I could turn this into two logs that are being subtracted, which is why you see what, well, there's subtraction between those, right? There's subtractions in the middle, and these are just numbers. So, I mean, there's a way to do it. You could do it all into one log. Well, wait, hold on. Yeah, this could come together to be all one log. I don't know why the computer does it that way. I mean, shoot, you know, I don't know. But again, human answer, right? Human answer, computer answer. Now they may have done the other method, you know, the other where they don't do that whole, like, let me make this turn into what. I'm sure the computer didn't do that. The computer is just running an algorithm, right? So, yeah. All right, let me see where we are here. So we just did linear over an irreducible quadratic, and we saw that that's a little bit messy. We have 10 minutes. I know we want to be done here. The next and last. That's weird. Huh. My whole computer just like flashed. Maybe that's a sign. All right. Linear over irreducible quadratic. Now, what if we have linear over repeated irreducible quadratic? Yeah. So that's a linear expression up top, isn't it? And that quadratic right there, x squared plus 1, can you factor x squared plus 1? No. Not plus 1. You can do x squared minus 1. You can factor that, but not x squared plus 1. So technically what's in blue there is irreducible, right? And it's a quadratic. And it's being repeated because it's being squared. Could we handle this? We play the same exact game that I just played. Stop.
Yeah, because you take the derivative, right?
I'm going to let u be the irreducible quadratic. And then what's the derivative of that? 2x dx, right? I sure do wish I had just a 2x dx up top. Right? I sure wish I did. And do I? No, right? I can split it. Well, I can split it, yes, but I'm going to stick to the same theme. So what I'm going to do is I'm going to rewrite this. I'm going to put 2 over 2, x plus 1 over x squared plus 1 squared dx, right? Why did I come in with a 2 over 2?
To make the 2x dx.
Yeah, to make this 2x happen. So 1/2 in front, distribute a 2 through the top, 2x plus 2, over the irreducible quadratic that's being repeated. And now I don't need to add or subtract a number because I have exactly what I want right there. That 2x is exactly the derivative of the bottom. But I am going to split it into 2 integrals. And my other integral's going to have a 1/2 in front of it. It'll have the 2, and then I'll have x squared plus 1 squared dx. Let me just back up. We had a linear expression on top. We had an irreducible quadratic on the bottom that was being repeated, but I followed the same method that I did in the previous problem. I let u be the irreducible quadratic. I took its derivative. I said, I really wish I had 2x up top, so I just multiplied top and bottom by 2 so I could get the 2x to happen. Unfortunately, when I do that, I also get a plus 2. So I split it into 2 pieces so that I get that integral I was really hoping for right here. And then that integral I'm going to have to find a way to deal with. But this one should be, I should be able to handle this. Because if I do my basic u substitution, what would this integral turn into if I use this u substitution? Yeah, I'll have 1/2, I guess let me include that. I'll have 1/2 1 over u squared du, right? That's what that would be? Not 1 over u du, 1 over u squared, because this is u and then it's squared. And that I think we can handle because you could do like power rule, right?
It's -2 to -2.
U to -2, so you'd add 1 and all that stuff.
Negative u, negative e to -1 power.
Yeah, exactly. We can do it, right? So we're like, okay, I can handle that one, all right? So I'm going to leave that one for now. We'll come back to it. This one's now the problem, right? And unfortunately for us, what's causing us, what's preventing us on this integral? Let me take that integral at the end. Let me pull the 2 out in the front, and that just becomes integral 1 over x squared plus 1 squared dx. What is preventing us from using formula 17? Yes?
Well, I was just going to make a suggestion.
Yeah, make it.
Can't you just do a u sub right here and scale it by
What would your u sub be?
the x squared plus 1?
X squared plus 1. What's its derivative?
2x?
Do you have a 2x somewhere?
No, but can't you? Oh, wait, never mind.
You can't scale by the variable. You can always scale by a number, but you can't be off by a variable.
So, but you can. Oh wait, no, I see what you're saying.
Yeah, the formula 17 does not have a squared on it, right? If that's not there, formula 17. In the previous problem, that's what happened, right? We completed the square, and we got formula 17. That's not formula 17. Can you what?
Can you make some imaginary 0 pop out of her?
Nope.
Can you do the square
You can
root
do the square root.
of, square root of x squared plus 1 to the 4th?
Oh, you want to rewrite this as the square root of that, all of that to the 4th power, and then do what? No, that's actually the right way.
Okay, I was gonna.
That's the right way to do it. So you're going to, because formula 17 doesn't work,
Yeah.
right? Because we don't have formula 17 here, we really kind of get stuck on this because we don't have a basic u substitution. You can't complete the square because this is already a completed square. You don't have an x term in the middle. Like there's absolutely nothing we can do other than to resort to the trig sub. I mean, we got to go to it. So we've actually got to see that this can be rewritten as the square root of x squared plus 1, but that whole quantity to the 4th power dx. Right? I mean, that's true, isn't it? I mean, that is what this is. And then I can use my trig sub. That sucks. But that's what I've got to do. And I'm out of time. No, I'm not out of time. I don't think I'm ever going to, in this class, get back to this one. That's, I mean, that we could do. We're still working on this integral. So I'm going to do a quick trig sub on this. What is the trig sub I do when I have variable squared plus constant squared? Tangent. A tan. What's A? 1. So this is tangent theta. X is tan theta is my u sub, or my trig sub, sorry. I'm doing trig sub. And then derivative of that is secant squared theta d theta. And the square root part that I'm not going to show the work for, that turns into secant theta. So that's what happens when I do that trig sub. I'm erasing all this. I hope you all understand that I've moved to the side. I'm doing like some scratch work figuring out what this integral was. The other one I circled, put a happy face. I still have to get that answer, right? But this one I'm working on like it's its own problem. So I'm going to rewrite this. This becomes 1 over, okay, this part right here is what? That right there is what? That's secant, right? That's secant theta to the 4th. So the bottom is secant to the 4th theta. And then what's dx? Secant squared theta d theta. This turns into 1 over secant squared. And that's cosine squared theta, which a lot of you didn't want to do this integral earlier today, right? That's a double angle. So this becomes a 1/2 integral 1 plus cosine 2 theta. And then you got to do the antiderivative of each of those. This is, yeah. It's hard to explain to people just how different Cal 2 is from Cal 1.
I don't know why, but like I said, I did terrible in Cal 1, but like Cal 2 is okay.
You're following? What I'm getting at is the extent to which you have to put effort in to get to the end of a problem. I mean, remember, next class, our goal is going to be do things and get them to look like one of these things today, right? Right? Like next class, we're going to be working on a problem. It's like, oh, if we can get it to linear over irreducible quadratic, we're like, whew, you know, but you see the work that's involved in it, right? Even when we get it to that point, it's still very involved. So it's like layers upon layers upon layers. I'm done. I'm out of time. You know what to do from there, right? You do the double angle. This is 2 sine theta, cosine theta. Then you got to go all, you know, from theta back to x. Out of time. So next class, you do not have any homework from this section tonight, all right? Because we're not ready for it. So in 12, what am I doing? 6.3. 6.3, there's no homework other than to go back into your notes or go research partial fraction decomposition. If you don't remember what it was, how it, what that is, partial fraction decomposition, that's what we're going to do next class.